All right. So welcome to the panel discussion. So we have 4 panelists here. The panel discussion will be on past and future of gravitational physics. So from my left to right, we have Professor Emeritus and the Director of Max Planck Institute in Potsdam for gravitational physics, Hermann Nicolai. Then we have Professor Kip Thorne, Nobel Prize laureate in 2017. Then we have Piran, and then finally we have Professor Valery Frolov. So according to the expertise, so Hermann Nicolai is mostly a string theorist and an expert on quantum gravity. Kip Thorne is mostly interested in gravitational physics, astrophysics, and many related phenomena. Piran is famous for his discoveries of in gamma ray bursts and in numerical relativity, and Valery Frolov is mostly known for his works on black hole physics. So now I will ask 3 questions for the panelists, and each of them will have an opportunity to respond. And then I will open the discussion for the audience. So then it will be your opportunity to ask questions after that. So first question regards the past, and the question is as follows. So what past discovery in gravitational physics or your area of expertise, it could be the quantum gravity, cosmology, or whatever, do you consider the most important, interesting, or impactful? And so maybe let us start from left. So Hermann, if you can start answering this question. Thank you so much.
Well, thank you very much. First of all, I would like to say I'm happy to be here and to honor the memory of Jiří Bičák, who was a frequent visitor to my institute. And I still remember, he spent extended periods of time at my institute. He always joined our discussions, and the remarkable thing about him was not just interested in his, specific questions that were in his field of expertise, but he had a really wide-ranging expertise or erudition, and so we could also discuss with him issues of quantum gravity. And he was always very interested of what the recent developments were. Now, you asked about exciting developments, just in my field, or more globally, I would say, of course, all the things that got Nobel Prizes, to start with gravitational waves, but also things like discovery of positivity of the cosmological constant, which, from my point of view, is really coming from supergravity and superstring theory. In that field, those theories have a very strong preference for negative cosmological constants. If you hear about what's going on in strings, there's lots about ADS. It's always ADS, and they have great trouble producing a solution that has positive cosmological constants. So from that point of view, this is interesting because it shows that we have our preferred theories, and then you look out of the window, it turns out it's just the opposite of what you think. So this in a more general area. Now coming to quantum gravity, you know that at this time we don't have a theory of quantum gravity. You have different ideas, different people have different preferences, and what is even more striking is that there's no consensus really in the community which is the correct direction to go. And part of the reason, of course, that at the moment we have no indication from nature what comes after Einstein or the standard model of particle physics. But just to mention one result that I found I was very impressed by is the calculations that have been done on higher order corrections in n equals 8 supergravity. N equals 8 supergravity is the most symmetric field theoretic extension of Einstein gravity in 4 dimensions. This theory has been around for more than 40 years, but to this date no one has been able to go beyond it. And therefore, it's a very important question whether theory is free of ultraviolet divergences. And back in the 80s, it was, completely unthinkable that anyone would actually do a calculation. But now what the people from UCLA, Piran and others have achieved is by completely new techniques, they've been able to push up the calculation to 5-loop order. And at that order, you have to, if you were to do things with ordinary Feynman diagrams, you would have to compute more Feynman diagrams than their cells in your brain. It's just mind-boggling. And they've been, over 20 years, they've been able to push this to 5 loops and show that the theory is finite to 5 loops, which was quite a surprise. But the challenge now, by the way, 5 loops, and they're now using these techniques actually to do gravitational wave calculations and gravitational, which is a sort of spin-off of what they originally did. But the challenge now is to go on and to find an argument whether it's really finite to all orders or whether there pops up a divergence at some higher order. But just to repeat, this was the result that from a technical point of view has impressed me most over the past 20, 30 years.
Thank you so much. Kip.
So I'll make some remarks about Jiří Bičák this evening in my public lecture, but let me just say that he was a dear friend, and it was such a pleasure to have him in my own research group on several occasions. I entered this field in 1962, which is before any of the rest of you were born, perhaps. It was a period where general relativity had for several decades been a backwater of physics, not much interest in it. And there were a few theorists who, including John Wheeler and Jordan here in Germany, and others who were pushing it from the theoretical point of view and trying to do a resurrection. But the thing that completely changed the field were a series of astronomical observations that came one after another over a period of about 1 decade. The discovery of quasars in 1963, and the gradual realization that they are powered by black holes with accretion disks. The discovery of the cosmic microwave background, and the very quick realization that it came from a hot Big Bang and would be a tool for exploring the birth of the universe. That was 1964, so 63, 64. 1967, the discovery of pulsars, and the fairly quick realization that these were the neutron stars, very relativistic types of stars, and that the physics of these objects would combine relativity and many other areas of physics altogether. The idea from Zeldovich and Novikov in 67, also in 67, that you look for black holes through looking for X-rays in compact binaries where you have a black hole orbiting around a companion star and gas from the companion star accretes onto the black hole. And the discovery and observations by the Uhuru satellite in 1971 of Cygnus X1 and the very gradual accumulation of proof that that is definitely a black hole of just the sort that Zeldovich and Novikov had pointed to. And this whole series of observations, as I say, transformed the field. Suddenly this field of relativistic astrophysics, the combining relativity with astrophysics and with cosmology, was hot. It was sexy. It was the thing that most young physicists wanted to work in, and I benefited from that. That was the story of the birth of my career.
Well, it's difficult to choose a single experiment, a single observation. So I'll talk about 3, and this is, of course, very subjective. The first one is the discovery of the expansion of the universe. This, I think, from philosophical point of view, sets us in a completely different framework. The fact that the universe is not static, it is expanding, it is changing, it's dynamic. For now, it is now kind of obvious. I mean, this is how it's supposed to be. But it wasn't like that. Remember Einstein's 1918 paper trying to build static cosmology. So this discovery is one of the most important ones, I think, in science. The second one, to me, that I'll mention is the discovery of the gravitational waves in 2015, the first detection of gravitational waves. But not because of the gravitational waves, because of the fact that it was a very clear indication, the first clear indication that black holes really exist. Black holes, as we think about them, and even beginning of seeing the oscillations of the horizon. And to me personally, it's why it is so exciting to me, the fact that we saw that black holes really exist. I'm slightly younger than Kip, but slightly older than most of you. When I wrote my PhD on black holes in the 70s in Israel, a great physicist, a really great physicist, was one of my not direct examiner, but he read my thesis and graded, and he said it's a very nice thesis, but it's not excellent. So in Israel, we have to have 3 reviewers should give it an excellent. And my supervisor tried to intervene because I don't believe in black holes. This was 76. I don't believe in black holes. In the next year or so, I went to the States as a postdoc. I gave a talk, again, a very distinguished, all know the name, relativist was in the audience. He later invited me to barbecue in his house. This was a great talk, but I don't believe in black holes. And this guy was a relativist. You all know his name. I won't tell either one. So for me, the fact that we are so close to the black hole and we almost saw the black hole vibrating was, well, you cannot say this statement anymore. And of course, there was the ETH observations later and so on. It's not an ultimate proof. There are still alternative theories, but we are getting there. So this is the second one. And now the third one. The third one to me is a failed experiment, or actually failed observation. And this is the failed 1914 eclipse experiments. There were 3 expeditions trying to measure the deflection of light during eclipses. Einstein was actually pushing for that since 1911. And there were three expeditions that failed, some because of war in Europe, and some because of weather in South America. The fact that this observation did not measure was an astonishing success for general relativity. Because if you all know, the prediction at that time was half of the amount that was of the correct amount, half of the amount that was measured later. It is difficult to imagine how history would have proceeded if this experiment would have worked. Einstein would, and others, but certainly Einstein was very close to the correct theory, but it would have looked like an epicycle. Without this evidence, GR is a much greater achievement, purely theoretical achievement, than if, or you have to add this factor to the equations to get things right. So to me, this was the third very important things very important observation in GR.
Thank you so much. Valerie?
I don't need this one or that one. Okay.
First
of all, I was very surprised to be included in the list of these famous scientists, and I don't know why David makes this selection, because there are present so many prominent scientists. After some thinking, my idea is that he wanted to have representative of as many countries as possible. So I'm representing Canada before it joined the United States. So maybe it's last opportunity to be Canadian citizen representing his own thinking about black holes and gravity. So it's very interesting to hear and be the last in this discussion, because it's interesting that we have different brains, but in many ways they are working in the parallel, so it's directions. So there is some kind of splitting of the problem in the parallel ways. And it's very interesting that when I try to think about this, practically there is a coincidence with other person's presentation. So if to speak about last 50 years, I've singled out 3 items. There are maybe much more, but first of them was Hawking discovering of quantum instability of black holes. So it's great theoretical discovery, and many people know everything about this. So it really was great work, which changes a lot of different branches of physics, because it happens that black holes serve as some kind of Rosetta Stone, where apply different branches of physics, thermodynamics, electromagnetism, strong gravity, combine them together, and to test validity of some complicated theory like string theory. So this string theory should produce the same entropy, which is given by the lowest order approximation Einstein gravity black hole entropy, or Gibbons-Hawking entropy. So in some things, it plays the role of the test for different fundamental theory, and this is a really great thing. Another thing is idea of inflation. So in some sense, it was a great idea which allows us to understand better origin of the universe, not coming in detail. Unfortunately, there are so many models of inflation that it's very difficult to choose, but basic idea is really important and great. And certainly the third one, but not the least one, is the discovery of gravitational radiation from coalescence of the black hole by LIGO. It happens on September 14, and it was under top secret for a few months until in February 11, as I remember, there was a press release when it will become available. There was some leakage of information, so rumors, but certainly this day, it was told that we observed collision of approximately 30 mass black holes. 10 to the minus 5 part of this mass is transformed to the strong gravitational waves, which reach us and was measured by LIGO. So to make it personal, I may say that it was one of the happiest days of my life. So a few personal remarks, why it happens. So I started my scientific career by being a third-year student of Moscow State University in '68. I first met my supervisor, Professor Markov, who at that time becomes interested in gravity, and he gave me a problem connected with semi-closed worlds, with black holes, and I fall in love with this subject, and till now it's my great love. At this time, I met him in spring of '68, and the notion of black hole, or nickname of black hole, was introduced in December of '68. Before this, it was different countries, different names for this. Frozen star in Soviet Union used some kind of general relativity objects and so on. After it was introduced, it becomes common. So, and at that time was quite interesting giving talks on the black holes in the seminars, because everybody liked these talks, but it was considered like a discussion of some fairy tales. So like, Alice come to the Wonderland, and what is great things there? And it was some kind of feeling that you're living in the Wonderland, and what are you doing? It's some kind of interesting, extremely interesting things, but very far away from reality. At that time, practically none of the astronomers believed in alien black holes. And as time comes, old astronomers died, new generation comes, they have fresh mining, and they become thinking about black holes more easily, and after discovering of this X-ray objects and so on, it becomes more popular. And it's interesting how during these 50 years it was shift of the understanding and vision of the black holes. So originally black holes were some kind of graves, and it was no hope to see this grave because they are small, emit nothing. But now we know that black holes are everywhere. There is a large amount of stellar mass black holes. There is a supermassive black holes in the core of galaxies, quasars, practically everywhere. So now we have a whole field with black holes. And this discovery of black hole by LIGO, it was some kind of trigger in understanding that we are dealing with something real, which really exists, and it was direct vision of what happens with this real object. And I need to say one very important, simple thing, but discovery of black hole, not only discovery of some new object, compact objects in the universe, it's discovering completely different state of the matter. All other compact objects are made of matter. In black holes, matter is used only to create black hole, and after it disappears, and we have only strong gravitational field. So it's some kind of soliton. And these solitons are living everywhere in the universe, and in many cases they may be important for dynamics of the galaxies, and maybe even to play the role of seeds for the galaxy formation. So this dramatic change during the 50 years is very impressive. So this was why I chose the third, this is a black hole stuff.
Well, thank you so much. So now, which brings me to the second question, which is about the future of gravitational physics. So what do you think the future of gravitational physics or quantum gravity or cosmology actually will be? Which direction the field will or should actually evolve? And maybe you can also include some advices for starting, graduate students or young researchers. Like, what would you recommend them to actually study? What do you think is most interesting, most promising, and should we involve AI in that process?
Should I start?
Please, Herman.
Well, as I already said, unfortunately, we do not have a theory of quantum gravity, and not yet. And so if I simply said to the student, well, go out and find the correct theory, that would, of course, be a nice problem to solve. But it is difficult at this time to give advice in which direction to go. I have my personal preferences, but as I said, there are several directions. And the current situation is such that the whole field is in a little bit of limbo, because no one really knows what the proper direction to follow up is. And as I said, as also already said, one problem is that we do not have a hint so far from nature what the correct direction should be that we should follow up. Meaning a clear experimental indication of something that's clearly beyond the theory that we know. On the one hand, Einstein's theory, and on the other side, the standard model of particle physics. So my first advice would be to a student, because this is a kind of question I'm asked rather often. My first advice would be, just follow your instincts a little bit. Of course, you should study as much as you can of what's on the market. And then the second advice would be, do not simply do things that just follow the mainstream. Do things because there are many other people doing this. Because I think the progress, if it comes, will probably come from a sort of direction that's orthogonal to the mainstream. We need some surprise, both from the theory side, and of course it would be even better if there was some big surprise from the experimental side. For example, discovery of a new elementary particle that would finally explain what dark matter is made of. That would certainly be something I would hope for. Because at the moment, you know, we make advances, our knowledge advances, but it's sort of very incremental. It's, you know, technical improvements here and there. There's nowhere at the moment, at least when it comes to quantum gravity, where we can say, that's it. And then the requirement would, of course, be that everybody agrees that this is the right thing. So as I said, if you're really courageous and if you really want to work in this field, just follow your own nose and do not simply do things because there are lots of other people doing these things.
Thank you so much. Kip?
Oh, hello, can you hear me? Yeah. Okay, so I see this field of gravity is now being extremely broad. It's changed enormously from when I entered the field. And there are so many opportunities in so many different directions. Each person has his or her own personality as a scientist, and different modes of operating are well suited to different people. I do not enjoy working in a large project. I had to because that was the only way LIGO could succeed. But I am much happier working in a small science mode together, either alone or together with 2 or 3 graduate students and a postdoc or 2. And so given opportunities in that direction, that's what I would choose to do in terms of style. But for those who really enjoy big collaborations, there are enormous opportunities in that direction as well. And for those who want to collaborate with artists and musicians and filmmakers, well, that's what I'm doing in my current career. All these are possibilities. I came to realize rather early that there is a big advantage in watching for unexpected opportunities and then thinking very carefully about them and deciding whether or not to take them. For me, Ray Weiss's invention and analysis of the gravity wave interferometers was an unexpected opportunity. I was very skeptical at first. It took me 3 years to become convinced that it had a chance of succeeding, and then I jumped at it. Working with somebody in Hollywood was not anything I ever expected to do, but I had an opportunity, and so I have. And so that's one piece of advice for young people is watch for unexpected opportunities, look broadly, and then a piece of advice that came from my grandfather when I was 4 years old. If you find a job when you grow up that's like play, then you'll be a big success. I came to appreciate that what he meant, or a big piece of what he meant, was that if you really want to make a mark on the world, you're going to have to work very, very hard. And if you don't find it fun, you probably won't be able to work that hard. So you should pick things that are fun and that have a possibility of then achieving some goal that you want to achieve. So talking about directions, of course, as I said, there are many directions one can go. One can work in the way that Jiří Bičák did, focusing on exact solutions or perturbation theory analyses, but analytic work, and there are enormous opportunities in that direction. And much of my career was also spent that way, and many of my students who work, for example, the Tucholsky equation for perturbations of black holes and so forth. There's tremendous opportunities in big collaborations on the Event Horizon Telescope or on future gravity wave missions in ESA or in LIGO and GEO and Virgo. There are great opportunities in quantum gravity. But let me just turn finally to the issue of what do I think is the most important thing to do. I never worked in it because it's too crowded, but I think that Herman's area of quantum gravity is the most important thing. It's it's the most fundamental problem. And if I were smart enough, far enough ahead of other people, I would have chosen to work in it. But I wasn't smart enough, so I chose other things. But I do see the tremendous possible opportunity in the observation of primordial gravitational waves. First, through their imprint on the polarization of the cosmic microwave background, the so-called B modes, which I think is likely to be observed definitively in the next 5 years, 10 years at the most, probably 5 years. And then in direct observations with a follow-on mission to LISA in the middle of this century. Gravitational waves are the only kind of radiation that can emerge unimpeded from the Big Bang and bring us information about what went on in the Big Bang. Of course, they get amplified by inflation, almost certainly, but that's a big advantage in the sense they get strong enough to observe. A disadvantage in some sense that you have to separate out the amplification effects from what actually came off the Big Bang. But for me, the opportunity to see then observational data from the Big Bang itself, where the laws of quantum gravity almost certainly were holding sway, and the possibility that the observational data will disagree with the standard theory that says nothing but vacuum fluctuations came off the Big Bang and they were amplified by inflation. The possibility that it will be different from that, and that will cause a huge breakthrough in quantum gravity and understanding the birth of our universe. This, to me, is really the most exciting hope for the future, and it's a future then that the younger people here are likely to experience. So that's something I would be particularly paying attention to.
Thank you so much. Sweet.
Well, looking around at the field today, the field of gravitational wave physics or gravitational wave astronomy is definitely something which will be booming in the next few decades, both because of new data and because of new ideas. And here, this is almost unlimited opening in various aspects, ranging from figuring out exactly the structure of the black hole that emit the gravitational waves while they are forming, to figuring out situations, astrophysical situations, in which are optically thick to everything, even to neutrinos, but gravitational waves can see inside and do, so you can see what's happening if you are sensitive enough. I'll give some examples like this in my talk tomorrow. So this is clear that it is, and the fact that new machines, new observatories are coming up, it means that there will be data. And something else that I'll mention tomorrow, that there is even semi-crazy ideas of building gravitational wave detectors on the moon to measure things that cannot be measured on Earth and use the whole moon as a resonant detector. It's a big bar, like a Weber bar, but a really big one. So this is clearly one field which is booming now and will explode when more and more data will be coming. A second direction is, which is to me very close to my heart, is the astrophysics of black holes in the center of galaxies. This was less explored than the astrophysics of solar mass black holes, which accretion on them was studied quite extensively since the discoveries of Cygnus X1 in the 70s. But now, what is really exciting is the combination of the black holes which are at the center of galaxies, and now we know that there are black holes in the center of every galaxy, and there are also swirls of stars around them. There are clouds of stars around them in the central nuclear clusters. And apparently the interaction between these clouds and the stars and the black holes is not trivial. There are tidal disruption events, there are embries. There are embries that happens when inside tidal disruption events of another star. We have seen some things like that recently. And there are collisions of stars in the vicinity of black holes, things that could not happen regularly, but because of the concentration of stars very close to the black holes, we even have collisions of stars around the black hole, which will cause a new type of transients which have not been identified yet, but are certainly going to be there. So the physics of all this complicated structure of a very center of a large mass black hole and the clouds of stars around them is definitely something to go into. And this is in combination with the fact that LISA will be launched and will measure some of this gravitational radiation coming directly from these events is a fantastic field. And having said all of that, we have to remember that there is an ongoing puzzle for more than 50 years. Since the first massive black holes were discovered in central galaxies, it was immediately clear that we don't know how they have formed. Because if you just take the usual argument of accretion and Eddington luminosity, you discover that the black holes these black holes do not have enough time to grow. And I think in '76, Martin Rees had a diagram of all the ways that how such black holes can grow. And if you look at the most recent publications today, reviews today, you see much fancier with fantastic graphics, diagrams, which are identical. And the bottom line of this diagram is that we don't have a clear answer. And the situation simply gets worse, and not worse, but more puzzling every year, because Webb is discovering massive black holes earlier and earlier. So this is another fantastic field to go to. And the combination of that I mentioned before, the issue of the interaction between the nuclear cluster, stellar cluster, and the black hole may have something to do with this. So again, this is a motivation to go for those of you of us who are interested in astronomy to go in that direction. But I completely agree with Skip that the big puzzle is quantum gravity. And the question is, that I agree with you, is to find the hint that will give us some clue to quantum gravity. I mentioned the failed experiments in 1914 before. The problem is that none of us in Einstein. Einstein could come up with GR without any hint. We need hints. We cannot come up with quantum gravity on our own. So the next thing that one can do is you can try to calculate quantum gravity from scratch, or you can try to look for these hints. And one direction to look for, and the only place that we can get such hints, as far as I can guess today, is from the universe. So one thing which Kip mentioned is gravitational wave coming from the early universe. But another thing is to look for anomalies in observations, for some things which could not be explained, which can be a very small effect and can hint towards quantum gravity effect. I'll give you one example in which I was playing, and every time that I play too much with it, my colleague tell me that I'm wasting my time and say, well, if something is found there, it will be great. It's the possibility, which arises in some versions of quantum gravity, that photons with different energies travel at different velocities in the limit that the energies, and this can be noticed in the limit that the energies of this photon is extremely large, that it is approaching the Planck scale. And remarkably, new very precise observational observations of transient phenomena can give limits on such phenomena. So this is one way, and unfortunately all the limits are now that this is probably not happening. But we want to be sure that this is not happening. And if we find something like this that is happening, this may be, it is possible that this will be a first clue to some quantum gravity effect. So this is one of the simplest quantum gravity effect. There are other effects like different propagation of photons, a different polarization, and so on, in vacuum, of course. This happens in plasma, but if you see something like this in vacuum, the two photons propagate at different velocities and so on, then so there is a growing field of search for astronomical observation that give hints on quantum effect, in which it's frustrating because you work and you find only upper limits. But the prize, if you find something which is not just upper limit, is enormous.
Thank you so much. Valery?
I will not be original if I tell that there are two clouds in our blue sky for cosmology and gravity, dark matter and dark energy. And we even don't know that dark matter have something to do with gravity. It may be a problem for astroparticles and high energy physics. And dark energy may be connected with gravity or not, but it's come to the question about modification of Einstein equation in the infrared domain at very far distances. So modification of gravity at the distances comparable with the size of the black hole can be tested using this LIGO data, and this is a lot of activity how this modification of gravity affect ringing radiation, all these details, and there's a huge amount of work on this subject. And from the theoretical side, I will say that there is one problem, and there is a set of connected problems with this. Unsolved problem is the final state of operating black holes. So when it comes to the state when the curvature becomes very high, of order of Planck, or maybe slightly less, we don't know what happens. And it's not problem that we are not working hard in general relativity. People are working hard at the Planckian scale physics, string theory, and so on. We don't have reliable theory there. And this is connected with a very general old problem of singularities and singular solutions in general relativity. So we know that inside black hole in the beginning of cosmology we have singularity, and how we need to treat this problem. So if you think about black gravitational field as quantizing, there is a fluctuation, and when we speak about some average gravitational field, we average over the fluctuation and use effective action approach to describe this smooth metric on the space-time. But if fluctuations are very large, you cannot use this language, and you come to the phase when you cannot use classical description of space-time. If gravity is emergent event, it happens because there is some kind of other phase, a string phase, or some other phase where instead of geometry, instead of metric, you will have some very complicated soup of different kind of strings and so on. We don't know what is it. Even if this is not the problem and you are looking from classical point of view, still there is a very important problem, namely, we use the language of space-time, and we, following Einstein, understand that we can measure these notions. We need clocks and rulers. But clocks and rulers are some devices which have structure. But when you have near singularity, curvature singularity domain, curvature infinitely grows. And for this reason, curvature is a tidal force. And tidal force destructs everything including your clocks and rulers. And if you don't have clocks and rulers, you have situation when you cannot use language of standard differential manifold to describe this domain of space-time. So how we need to consider this problem? We may say that space-time terminates its existence in some domains. So we still can live with this, or we say that we don't like this, we try to escape this. And there's plenty of work now on so-called regular black holes and all these kind of things. Idea is the following, that it may happen that there is some principle that when curvature becomes large, actions of Einstein is modified by quantum gravity correction, by anything else, so that effectively curvature cannot grow beyond some limit, and space-time picture remains valid. So in this case, you resolve singularity, but you have very interesting problem and opportunities. Namely, inside the black hole, you may create a new universe. And what we can see as a remnant of old black holes will be white hole in our universe. So David told me that not to restrict ourselves with some kind of very physical things, you may have some kind of imagination. So my imagination is that, for example, if the universe is contracting and there were plenty of black holes, they pass through the regular state, something like de Sitter-like state, and there is a new universe created with some number of what we call primordial black holes. And maybe in this scenario, you can create primordial black hole, not from fluctuation of the radiation and the early universe, but it will be just come as a memory of the previous universe. So the question is that, is it possible to trace that something come from other universe, or are there any conserved quantities which tell us of this? But this kind of opportunity exists if you just consider situation that you would not like to terminate space-time. So there are many other problems connected with observation, and all problem is the existence of primordial black holes. So as soon as Hawking told about this radiation and emission of the radiation from black holes, it becomes possible that small black holes may disappear, but can these small black holes be created in the early universe? If they are phase transition, they can be created from inhomogeneities. But if they are created at the early stage of the inflation, they will be diluted, and we shall not meet them in our universe. So if a transition happens at the end of inflation, you can see some of these remnants, some primordial black holes. Question, what kind of phase transition? Do they really exist? Can them observe? Another object which is have some formally strong gravitational field is the core of the cosmic string. And cosmic string are specially topologically stable solution which are predicted by the phase transition in the thermal gas when it's some kind of phase transition happens. So this is a prediction of the theory, but we have not seen, as far as I know, indications that they exist. And we cannot forbid their existence from observation. So only we can say that heavier than something contradict some of our observation. And finally, if not restrict fantasy, there is a question of the following type. Einstein opened Pandora box. So variety of solution of general activity is wide. And we are living in the world when only small number of these opportunities are realized. So what kind of opportunities? Non-trivial topology. So you can have wormholes. You also have non-trivial causality. So it's time machines and so on. So there was a lot of discussion of this kind of things. Usually they are unstable or require some kind of unusual matter. But you know that after discovering of the black hole after 100 years after prediction in some sense, I will not be so astonished if some kind of wormhole suddenly will be found and we find out that some kind of very, under special conditions, it's possible to have wormholes which are self-supported. Also, there was an old paper of Wheeler and collaborators about geons. It's self-trapped gravitational field. You have photons, gravitons moving around some center, and the gravitational field can support this object. and there is a time like it will be decaying, but in principle, this kind of objects can exist also in our universe. So in some sense, there may be interesting new objects which are predicted, described in general relativity, but still not opened. And this is one of the interesting things to think about in future.
Well, thank you so much. So my last question was going to be about the technological applications of general relativity. So namely, like I have seen many courses on quantum mechanics which start like, well, we have two pillars of modern physics, quantum mechanics and general relativity. Now, quantum mechanics underpins so many technological applications. It stands behind electronic microscope, solar cells, atomic clocks, lasers, MRI, whatever you name it, right? Now, the applications for general relativity are GPS. Okay, do you see any potential technological applications for general relativity, maybe in the future? Very briefly, please.
That's the difficult question. For me, because I'm really millions of light years away from the real world. But you know, I think you know what people do in connection with gravitational waves. I mean, all the technology that's being developed there. I'm sure that will have some spin-off. On the more theoretical side, if you think about the calculational techniques that we need to develop for gravitational waves, but also in particle physics for higher order corrections in scattering, this also helps us to deal with large data, to manage large data, and this is surely something that's of very general interest. Let me just tell you, you know, I started working out in supergravity. In those days, it was long calculations. I still remember sitting for weeks and weeks and weeks and trying to figure out what the Lagrangian was, and it was really invariant. And now the technology, the theoretical technology has been advanced to such a stage that if I take that old problem, go to my PhD student and say, can you please check this? Then he pushes a few buttons on the computer and I have the answer in 3 minutes. So I would say that's real progress. And I think in, you know, as a technology for solving general problems, not just physics problems, this is certainly very valuable. And I can also tell from the fact that not all of my students end up in academia, but many of them end up in counseling business and applying the algorithms to, I don't know, stock market very successfully. So that kind of application I can imagine coming from the purely theoretical side. But I think with the experiments, of course, there's a much larger field of possible applications.
Thanks. Kip, do you want?
Okay, well, taking off from what you said, Herman, in fact, historically, the origin of modern quantum sensing technology, it's sometimes called quantum precision measurement technology, but the technology to make measurements that circumvent the Heisenberg uncertainty principle, measurements that manipulate the quantum state of the system that you're measuring in the process of making the measurement. This is a 21st century technology that's a close cousin to quantum computing and quantum cryptography. And it arose from LIGO because we had to have it in order to have a high probability of success. I'll talk about that this evening a little bit. So I think, and it was initiated hand in hand with quantum computing. The first step in quantum computing was Richard Feynman's lecture, famous lecture, where he argued that if you build a computer that was based on quantum logic, it would have enormous power for certain kinds of problems that classical computers couldn't have. And that was the beginning of quantum computing. Feynman was a close colleague of mine in my research group. And he and Carlton Caves and I, who were talking with each other in the same period as Caves invented the technology for quantum sensing, quantum precision measurement. And again, as I say, I'll discuss this to some degree this evening, but I think this field has already given rise to technology that's going to have a huge impact. But it's not relativistic technology, it's the quantum technology that we required in order to have success.
Thanks. Zvi, do you want to react?
Well, actually, you mentioned GPS, so, and I mentioned the 1914 experiment. It would have been amazing if Einstein did not suggest GR in 1915. It's not clear if it would have been invented on purely theoretical grounds for another 100 years. Then military technology will come, and the guys will begin to develop GPS. And then they'll discover that there is a secret, then GR, or some version of GR, some approximation of GR, would have been discovered in some laboratory, in some weapon laboratories, and kept as a secret, as a complete secret, because this would have been an essential secret. And it would be amusing to think about how long it will take for the secret to leak out. And moreover, it will be amusing to figure out how from the anomalies, the GPS anomalies, how could one work out that actually we have G mu nu in the background? Because it is not trivial at all to go from this observation backwards. So you're right, GPS is the only direct technology. But let me tell you something which is actually connected probably with what Kip just said and was said before. And I came to my first visit or second visit to Japan in '68. Takashi Nakamura, that some of you may know, told me that Sony, which was at that time one of the biggest technological companies in the world, this was before the days of Apple and Microsoft, that Sony had a special department of one person on gravitational waves. They were trying to follow all the technology that at that time, this was even before LIGO, at that time was developed to measure gravitational waves to see if it has technological implications. So this is a far-sighted view how to treat this problem. I will not go on and continue to mention kind of byproducts. But thinking directly on gravitational physics, I'm surprised that nobody mentioned yet time machines. This will be the impact of gravitational physics on the world that we live. When will it be? Ask Kip. But this is really the place that I could see that gravitation could influence us directly, because gravitational waves are simply too weak. But let me mention something else about gravitational wave, and this is something that Freeman Dyson actually wrote several articles about. It's the fact that it's the question, can we measure a single graviton? In electromagnetic physics following quantum gravity, it is obvious that we can measure single photons. We have devices that measure single photons, and we can see when a single photon is absorbed by an atom. But Dyson was showing the difficulties or the impossibility, almost impossibilities. He has some no-go theorems, that it is impossible to build a machine that will detect a single graviton. So single graviton physics or experimental single graviton physics, if we reach there, may have some unimaginable consequences, if this can be reached. This is actually something that may influence Earth. There are some steps, unexpected steps in this direction by attempts to build megahertz gravitational wave detectors, detectors of gravitational radiation that are at the megahertz regime. The only problem there, in my mind, is that I cannot imagine any source that can produce megahertz gravitational waves. So this is so it's fantastic. There is a fantastic development of detectors of something that I would say, I won't say nobody, because but at least I don't know what kind of sources can produce them. So if you build such thing and you measure something and it is not a mistake, it is great. And yeah, I think this is some of the directions. And I think that if we manage to build a time machine, it will make some strong impact on the life of us.
Thank you so much. Well, let's build it. Valery, fast reaction.
So it's a real story. When my son was...
You were in a time machine?
No. So when my son was small and was coming to the kindergarten, I told him about time machine, and his response was interesting. Yes, it can be done, but it will be so expensive to travel in time that nobody will have enough money to do this. So it may happen. But now about David's question. I interpret it in a slightly different manner. So can we use something from strong gravitational field to be useful for technology and industry? And to answer this question, I remind you a well-known story about Faraday. It was 1831. He was giving a talk about unification of electric and magnetic fields and electromagnetism. And one skeptical politician asked after this talk, how can you use this, your electromagnetism? And Faraday answered that, I don't know how to use it now, but I'm completely sure that there will be a day when the government finds a way to tax it. So David is not skeptical politician, I'm not Faraday, and my answer about using strong gravitational field is negative. So I doubt that in the next 50, 100 years, it will be done only in some kind of science fiction situation. For example, primordial black hole of mass 10 to the 20 gram will be found not far from the Earth, taken close to us, and used as a device for the energy power. You throw matter, obtain radiation, and use it. Or if you have large rotating black hole, you can use it, Penrose effect, to boost your rocket to higher velocity. But it's some kind of fantastic thing. In reality, I doubt. And in fact, there is other more general question. So part of us were living in the second part of the 20th century. All of us are living in the first 25 years of the 21st century. And we are living in the wonderful time when there was a great development of science in many different directions. One time I remember Werner Israel told me, Valery, enjoy this time. Government are paying us money for what we do ourselves. So, I don't know how long it continues. The problem is that the source of the money is limited. The number of problems for human beings is growing. So there is a problem of survival, health problem, and so on. Artificial intelligence will create for us some kind of artificial world and operate with our desire to know something new. And I don't know how it affects our general knowledge. But it may happen that in 50 years and 100 years, nobody will care about the beginning of the universe, about the origin of quantum gravity. So it may be, this will be they will remember this is a golden time of our science. I hope it will not happen, but it maybe we a little bit exaggerated living in this kind of interesting time, and we are thinking that it continues forever. It may happen that it stops some time, and people will orient their interest to some other direction. But nevertheless, we must be very happy with this. Thank you.
So with this pessimistic point of view, let us finish the discussion, and I ask you to postpone your questions for the coffee period. So we will start like in maybe 4:20 or something like that, the last section.